Hello and welcome everyone. We're happy that we are all together again. In this tutorial, we will start our journey in the lighting system design. So this is a very important tutorial because we will discuss some important basics that will be the core of this section for anyone who wanted to understand how to design any lighting system. So fasten your belt and let's get started. The aim of this tutorial is to learn some basics related to the difference between the interior and the exterior lighting system designs, and also we will discuss some definitions related to the lighting system in general. So let's go ahead. The first basic question now is that, what is the first step of any lighting system design? And here the answer is that when we start any design for any lighting system, we must know firstly what is the nature of the place that we need to make the design for it. So we need to specify firstly the type of the place. And for that we have two kinds of places that we need to make the lighting system for them. The first one is called the interior design, and the interior designs are some designs like that home here in that figure. And the second type is the exterior lighting system design, as you see here, this design for the outdoors. So according to the type of the lighting design, we will specify the steps of the design. And this is because the steps of the outdoor designs are different from the steps of the indoor design. For example, there are some lamps that are used outdoor, but we don't use them indoor. Also, there are some lamps that are used in the interior design, but we cannot use them for the exterior design. This is because those lamps are designed mainly to be used for the indoor design, not the outdoor. So if we specify the type of the design to be interior or exterior, the next step will depend on that type. Alright, now let's start with the interior design. As we said, the interior lighting system design is any design that is located inside the building in case of closed buildings. So for any closed building, the lighting system design for it will be an interior design. And an example of that is that mall here. And also if we are making the lighting design for this closed basketball court, so this is an interior design also. And the same thing if we made the lighting design for this lecture hall, so this is another example for the interior design. Alright, now let's go to the second type, which is the exterior lighting system design or the outdoor design. Here its definition is the inverse of the interior design, as it's any lighting design that is located outside the building in case of closed buildings. So for any closed building, any design that is located outside it will be an exterior design. And an example for that exterior design is the parking outside the mall, for example. So the street lighting outside the mall is an exterior lighting design. But we have another definition for the exterior lighting design, which is any lighting design that is located inside the building in case of open buildings. So for the open buildings, any lighting design inside it will be an exterior design. For example, the lighting design for the football stadium, it's an exterior design. This is because it's an open building, although the design is inside it. And also if we have an open basketball court, so its lighting design now is an exterior one. This is because it's an open area. While if you remember on the previous example, the basketball design was an interior design. This is because the basketball court there was in a closed building. So according to our case, we specify the design type. Very good. Now let's jump to some concepts related to the lamps that we will use in our design. So the first definition we need to discuss now is the luminous flux. So the luminous flux is the quantity of light emitted by the light source for a period of time, and its unit is lumen or Lm. So if this is a light source, so the quantity of light that is emitted by that light source for a specific period of time is the luminous flux. And its mathematical relation is that one. Here the symbol of the luminous flux is phi, and it's equal Q over T, where Q is the quantity of light emitted and T is the period of time that this quantity of light is emitted at which. So this idea of the light emitted is similar to the water that is going out of the faucet, as the water represents the light or the Q in our example that is going out of the lamp at specific time. So there is a faucet that has a large amount of water going out of it, while another faucet permits a small amount of water to go out of it. So the lamps have the same idea, as each lamp has a fixed value of lumens that it can produce. So some lamps have a smaller value of lumens emitted out of it, and some other lamps have a higher value of lumens emitted out of it. Very good. Now the second parameter related to the lamps is called the illumination or the lux of the light source. So the lux is the number of lumens falling on the surface per unit area. So we can say that the illumination is the relation between the lumens emitted from the light source over the area that those lumens are falling on. So the illumination is represented by the letter E, and it's equal phi over A, where phi is the lumens that we have just talked about, and A is the area that those lumens are falling on. So suppose that we have that light source that emits some amount of light. At that condition, the lux or the illumination at that surface will be 2000 lux, while the lux at that larger surface will be only 500 lux. And you can notice, although we have the same light source, but the illumination is different from the first area to the second area, and this is because the lux depends mainly on the area that is falling on it. As when the area increases, the lux will decrease. This is because the lux equal phi over the falling area. But you know, the illumination can be determined also at a specific point, not at a specific area. So if we need to calculate the illumination at a specific point, here its relation equal I times cosine theta of the power 3 over h of the power 2. I know that you don't understand anything from this relation until now, but we will break it into some simple pieces to understand it. Here I is the amount of light emitted from the light source, and it's similar to the lumens, but it's another parameter here that is called the lumens intensity, and we refer it to the letter I. And this I or the lumens intensity is an expression of the amount of light that is emitted from the light source. And also its unit is candle, so we measure it with a unit of candle. So this is about the first parameter I. And then h is the vertical distance from the light source to the surface at which we need to calculate the illumination or the lux. And then theta is the angle between the vertical line and the line that connects the light source to that specific point that we need to get the lux at it. So if we need to get the lux at that point, it will be the candle emitted from the lamp times cosine theta of the power 3, where theta is the angle as you see between that vertical line to the light source over h square, which is the vertical line here. But this is about the mathematical point of view. And now we need to know practically what is the difference between the illumination or the lux and the luminous intensity phi. So we need to know for our design that we will implement what is the difference between E and phi. Now suppose that we have this light source on that sleeping room. So the lux at that condition is the amount of light required to exist in the working plane. So each type of places or each room will need a specific value of lux to exist on. And we get this value of the lux from some standard codes like the IEC code, and this is a screenshot from an international code of the lux that is required for some places. As you see, the general office, for example, needs 500 lux, while the business machine office needs 750 lux for it, and so on. So those are the required values of lux or lumens to fall on the surface per unit area. But on the other hand, the luminous flux or the phi depends on the lamp type itself, regardless to the type of the place that we need to design the lighting system for it. So it's the amount of light emitted from the lamp itself. And we get this value from the lamp datasheet, as the lumens are specified in each lamp datasheet. You can see here each of those lamps has a fixed value of lumens of 1600 lumens, so we get the lamp lumens from the catalog of the lamp, as it's considered as a specific feature of each lamp. But you can see also, although each lamp produces 1600 lumens, but the first lamp consumes the largest power of 100 watt, while the second lamp consumes only 77 watts, and the third lamp consumes 23 watts. And lastly, the last lamp consumes only 20 watts. So this leads us to another concept, which is the lamp efficacy. So the lamp efficacy is the ratio between the input power of the lamp to the output lumens that is going out of the lamp. As each device has an input and it produces an output, so the input of the lamp is the power in watts, while the output of the lamp is the light in lumens. Or in other words, the lamp converts the electric power to a light output of it. So the efficacy of a lamp is the ratio between the input power to the output lumens. And by that value, we can specify the efficacy of each lamp. For example, we can have an incandescent lamp that consumes 40 watts and it produces 55 lumens. So its efficacy at that condition is only 14. While another compact fluorescent lamp can produce some lumens of about 550 watt, but with an input of power of 9 watts only. So it's very obvious that the compact fluorescent lamp is more efficient, as its efficacy is larger than the incandescent lamp, as here it's 61. On the other hand, another LED lamp can consume only 7 watt, but it produces 400 lumens. So its efficacy at that condition is 75 lumens per watt. So what we want to say is that the higher efficacy, the more better is the lamp. More than great. So that's about this tutorial. Hope that's clear right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. Very happy that we are all together again. And this tutorial will continue illustrating some concepts related to the lighting system design, as we are preparing ourselves now with all the needed fundamentals to use in our new design that we will implement. So fasten your pull and let's get started. The aim of this tutorial is to continue understanding some basics related to the lighting system that will help us greatly in the lighting system design. So let's go ahead. First of all, we need to know what is the color rendering index. Here this term is very important as we will use it much later, so let's discover it. As you see, we can illustrate with that figure. Those are not 4 different apples, but this is one apple and we have taken a photo for it 4 times. But what it changes only each time is the light that is applied to that apple when we are taking the photo for it. So this means when the light source changes, the color of the object that is applied to that light will change. And this is because each light has a different color that is different from the other light sources. And for us to specify the color for each different light, we have defined this definition of the color rendering index, or the CRI, that represents a percentage from 0 to 100% to specify the color of the light. And for us to specify the color for each different light, we have defined this definition of the color rendering index, or the CRI, that represents a percentage from 0 to 100% to specify the color of that light. For example, when we apply this apple to a specific color that has a color rendering index of 70%, it will appear with that color. While when changing the light source with another light that has another color rendering index of 80%, it will appear with this dark shape. And also when we change the light source with another one that has a CRI of 90%, its color will be changed to appear like that one. And finally, when the light source has a CRI of 97%, the apple will appear with that color. And we have a notes here. You can notice when the color rendering index value increases, we are getting a more true vision of the object, while when it decreases, the color of the object changes compared to its original appearance. So when the CRI is getting nearer to 100%, you see here it's 97%, so the apple appears with its true vision or its true color. While when the CRI is very low, like the 70%, so the color of the apple has a great difference from its normal condition. So we say that the color rendering index is the ability of the light source to show true vision as seen outdoor on the sunlight. And here we are considering the sunlight to be the reference, so the true vision of any object is achieved at the sunlight, so the CRI of the sunlight is 100%, and we are comparing the other lights with the sunlight to get its color rendering index. So the more the lamp light is similar to the sunlight, the higher the color rendering index. And here are some lamps type with their color rendering index or their different values for color rendering index. So the incandescent lamp has the highest CRI of 100%, while the fluorescent lamp has a lower value of CRI of 85%, and the same thing for the metal halide, it's 85, and the coated mercury has a lower value of 49, and then the pressure sodium or the high pressure sodium has a value of 24%, and the clear mercury value is 70%, and finally the low pressure sodium is the lowest one, or it has the lowest CRI of only 5%. So at conclusion, we want to say that the higher CRI, the more better is the lamp, as it produces a color that is nearer to the true vision as seen in the sunlight. That's great. Now let's move to another definition, which is the color temperature. So we need to know what is the color temperature. You can see here, for any lamp to produce a light, a part of the electrical energy is converted to a heat. So according to the temperature of this heat, there will be a color produced from that light. So when the temperature of the light output is 1000 Kelvin, for example, the color produced will be red, while when the temperature is, for example, 4000 Kelvin, the color output of it will be yellow. And when the temperature increases to 1000 Kelvin, the color output of the light will be blue, and so on. So according to the temperature of the light, the color output will change. So we can say that the color temperature is the color produced from the light source according to its temperature. Alright. Now you can see this is the scale of each temperature that is produced from each light. So the natural candle light is about 2000 Kelvin, while the incandescent lamp has a light of 2500 Kelvin, and the sunlight color temperature is 5500 Kelvin. And on the upper here we have the LED lamps that produces a light that has a color of about 7000 Kelvin. So what we want to say is that each lamp produces a specific light, and each light has a specific color, and each color has a specific temperature related to it. Very good. Now the last concept we have in this tutorial is the stroboscopic effect. And I can tell you that the stroboscopic effect is a very important effect that is related to the lighting system design. So let's illustrate it. Suppose that we have this light source, and this light source is powered by the alternating current, and the alternating current changes its magnitude and its direction each cycle. And also we know that the frequency of the alternating current is 50 or 60 Hz. So suppose that we are working on the 50 Hz frequency system. So this means that this sinusoidal waveform will repeat itself 50 times or 50 cycles in each second. Do you imagine? The voltage waveform changes its magnitude 50 times in each second. So it reaches the zero level and its maximum level or its peak level 50 times in each second. And that means when the voltage reaches its maximum value, so the lamp will have a maximum output light, while when the voltage waveform reaches its zero values, so the lamp will produce no light. But you may ask, why we don't see the lamp when it becomes off or when there is no light out of it? So the answer is that this operation of getting on and off is very fast. As we mentioned, this cycle repeats itself 50 times in each second. So each cycle lasts 0.02 seconds. And for that your eyes can't note the lamp when it's getting off. But instead of that you see the average of the output voltage. But the thing here is that when that light with this frequency falls on some rotational parts with higher frequencies also, so those parts may appear to be rotating in the reverse direction. And for that you will get a wrong vision of some moving objects at that case. And this is the stroboscopic effect, which is a visual phenomena that occurs when a continuous motion is represented by a series of short instantaneous samples. So at conclusion we say that when the light output from some lamps that has some specific frequencies falls on some moving objects, those objects will appear to have a different moving technique from their true moving technique, and this will be a dangerous thing in our case, as you will get a wrong vision for the objects which may harm you as a human. Very good. So that's about the stroboscopic effect and some concepts related to the lighting system design. Hope that's clear right now. Thank you for watching and see you next tutorials.